Hello dear students, hope all of you are doing well. Welcome to the second channel of SBM. I am Subhas Vera. Today I will discuss to you the number system, and this is the first chapter of class 10, which is marked as NCERT recommended books. And you know that the number system includes in your chapters are real numbers. Before jumping into the real numbers directly, first we will understand what we are going to discuss today. Today we are going to discuss natural numbers, whole numbers, integers, rational numbers and irrational numbers a little bit, and then we will go to the Euclid's lemma and algorithm and its application, and fundamental theory of application and its application as well. What is the need of learning that natural numbers and whole numbers? Because the real numbers which contains all of these numbers, if we do not know the what is natural number, what is whole number and how they act in our applications, then it will be difficult for us to understand the whole number system. This is why first we are going to recap our natural numbers and whole numbers, integers and rational and irrational numbers, what we have learned in our earlier classes, right? So let's get started. First we have natural numbers, or we can say that counting numbers. What are the natural numbers? I have already written that the numbers which are used for counting objects. Suppose you are given with some objects, whatever object is, it can books, it can pens, whatever it is. Now if I asked you that count the numbers, how many books are there, how many pens are there, you will start counting from 1, 2, 3 and so on, like that, and we will get a result, that is that there are 10 books or 12 books. Now these types of numbers, that is we are used for countings, these are called the natural numbers. And we never started counting from 0, 1, 2, we never started counting like that. So we started counting numbers from 1, 2, 3 and so on. This is why the numbers which we use for counting objects, that can be living object or non-living object, that does not matter, these are called the natural number. So natural number includes the number 1, 2, 3, 4, 5 and so on. There is no upper limit for these numbers, it can go beyond infinity. If I talk about infinity, infinity is a concept which describes a large number which has no limit, actually which has no limit, it's boundless number and denoted by that sign, that is horizontal 8, right? It looks like horizontal 8. This is infinity, and it is a concept of a large number. Actually it is not a number, it is a symbol which represents limitless. And this circle represents the numbers which are what we call natural number, that is in between circle I can write 1, 2, 3, 4, 5 and so on, these types of numbers. And today we will understand that how the numbers, natural numbers, whole numbers and the other numbers are interrelated, right? So next jump into the whole numbers. What are the whole numbers? Whole numbers are the all natural numbers together with 0. We have already understand that what are the natural numbers, 1, 2, 3, 4, 5 and so on, these are called the natural numbers. Now if we include the 0 with it, it will get the whole number. So what is whole number? Whole number is all the natural numbers together with 0 are called whole number. So we can easily understand that in whole numbers there is a additional number which is 0, which is not included in the natural number, and we have already known that the natural numbers include 1, 2, 3, 4 and so on, these types of numbers. This is the concept I want to make you understand, that in the green circle we are denoting the whole numbers, and in the pink circle I am denoting the natural number. So in between natural numbers there is no 0, and in whole number there is 0 included. So we can say that in notes I have told you that all natural numbers are whole numbers, but not conversely, because whole number contains an extra number, that is 0, which is not included in the natural number. That's why we can say that natural number is a subset of whole number. Now if, all of you who knows the concept of set, you can easily understand what is subset, and if you don't know the concept of subset or sets, then it doesn't matter, no problem, you can easily understand that the all natural numbers are whole number and not conversely, right? Next jump into the integers. Before understanding integers, you have to understand what is negative of a number. Suppose you are given with a number 5. Now if I ask you what is negative of the number 5, now if you, as you know the concept of integers, actually integers are teach to you in class 8 or 9, so you have already known to the fact that what are the negative of a number. Now I have quickly recap you that negative of a number is a number which has same absolute value as of a positive number, in that case it is 5, but resides on the left side of 0 on the number line, maintaining the same distance from 0. Now if I talk about the number line, we take that 0 as middle and 1, 2, 3, 4 and 5, all the positive numbers will I write on the right hand to the 0, and if we write the same numbers 1, 2, 3, 4 and 5 on the left of 0 and mark it as a negative sign before that, then that will represent the negative of the positive numbers and they will be equally distant from 0. Now if I talk about 5, now 5 is that distance from 0, and if I talk about the negative of 5, that is -5, which is also the equally distant from 0. So the numbers which has same absolute value, in that case this is 5, and resides on the left side of the 0 and maintaining the same distance from the 0 are called the negative of number. Now this will help us understand the integers. Now what are the integers? Whole numbers together with negatives of all natural numbers are called integers. Now we have already understand that whole number includes that the 0 and the natural numbers. Now if I include that the negatives of natural number, it will give us the integers, and if you look into the diagram you can easily understand what are the integers and what it includes, right? We have already understand that the green circle represents the whole number, that is including 0 and the natural numbers. Now if additionally we include the negatives of the natural number, that is -1, -2, -3, -4 and so on, this will give the square box or the rectangular box which will represent the integers. Then easily we can find that, and it is easily understandable to the diagram that integer includes all the whole numbers and natural numbers, but all integers are whole numbers, because there are integers which has negative value, that is -1, -2, which are not included in the whole number. This is why I make a note that all whole numbers are integers, but not conversely, that is all integers are not whole numbers, right? The positive integers are called whole numbers, right? So we can easily understand the integer. Integers are also divided into two parts, that is positive integer and negative integers. The number which resides on the right of 0 are called positive integers, and the numbers which resides on the left of 0 are called negative integers. Now what about 0? 0 is an integer but neither positive nor negative, so 0 is called non-negative and non-positive, non-negative and non-positive integer, right? At the same time it is non-negative, at the same time it is non-negative integer, right? Hope integers are clear to you. Next, if I talk about rational numbers, the numbers which can be put in the form p by q. Now you have to understand what is the significance of p and q. P and q are integers and q not equal to 0, that is the denominator must be non-zero, because the denominator, if the denominator is 0, then that will be undefined number, because we cannot divide a number by 0. This is why denominator 0 does not make any sense. Now these kinds of numbers are known as rational numbers. So the numbers which can be put in the form. There must be a question in your mind that whether the integers are rational numbers. Yes, definitely, because if we write the integer 5, we can write it as 5 by 1, so we can put it in the form p by q. Also you can write 5 as 10 by 2, also you can write 5 as 100 by 20. So in different ways we can express the integers as a rational number. So all integers are rational number, there is no doubt. We can also put the 0 as 0 equal to 0 by 5 equal to 0 by 10 and whatever. There are different forms in which we can put the zeros. So all integers which are in the form p by q, that is all are rational numbers, but not necessarily all rational numbers are integers. So there must be some additional numbers which are rational but not integers. What are they? The numbers are like the decimals 1.4, 3.2, minus 12.4, minus 0.6, and like there are numerous numbers. That is, if I talk about the numbers in between 1 and 2, there are numerous numbers, that is 1.2, 1.3, 1.5 and so on. So we can put infinitely many numbers in between two integers. So these types of numbers together with all integers are called rational numbers. Now there might be a question in your mind that how decimals are rational numbers, whether they can be put in the form p by q. Yes, I can definitely assure you that 1.2 can be put in the form 12 by 10, because we already understand that smart method of division, that is division by 10, 100 and 12, that is decimal point will be put on the from right to left after the number of zeros on the denominator, right? You have already that you have understand in your lower classes like 5 or 6, right? So all decimals can be put in the form p by q. So all decimals are included in the rational number. So what are the rational numbers? The number that can be put in the form p by q where denominator not equal to 0 and the numerator and denominator must be integer, right? These types of numbers are called rational numbers, and rational numbers includes all the 0. Now there is a note, all integers are rational numbers. I have already mentioned that because we can put all integers in the form p by q. So all integers are rational number, but not conversely. Conversely it is not true, because there are some numbers which are decimal numbers which can be put in the form p by q, but they are not in the form of integers. Like if you look into the diagram, the outermost diagram, that is the ovaloid rectangle, you can easily understand that there are some numbers which outside the square or the rectangle which are not included in the integer section, right? We have already discussed in the earlier section that the integers are described in the rectangular shape, right? So we can easily understand that these types of numbers which can be put in the form p by q are called rational numbers. Now if I talk about irrational numbers, what kind of numbers are irrational numbers? The numbers that cannot be put in the form p by q, which is the exactly opposite definition to the rational number. Rational number says that the numbers that can be put in the form p by q are called rational number. Now if we do not put the numbers in the form p by q, this will not gives us the rational number. Now what kind of numbers are they which cannot be put in the form p by q? Because we have already understand that decimals can be put in the form p by q. So what kind of numbers we are left with? We are left with the numbers root 2, root 3, that is square root of non-perfect square number. Now there are different non-perfect square number 2, 3, 5, 6, 7, 8, 10, 12. There are numerous non-perfect square numbers. These non-perfect numbers, if we take the square root of these non-perfect numbers, that is root 2, root 3, root 6, root 8 and so on, this will gives us the irrational number. We cannot put it in the form. Now you can tell me that we can write root 2 as root 2 by 1. Yes, we can write, but the condition is pq must be integers. Here p is root 2 and q is 1. Definitely q satisfies its condition, but p does not satisfy its condition because root 2 does not include in the integers. This is why if these kinds of number cannot be put in the form p by q. This is why this is irrational numbers. Also there are numbers transcendental irrational number, that is pi and e. Also there are numbers which is non-terminating non-repeating decimals, that is the numbers which makes an rhythmic upgradation. That is here the first 1 2, then 1 double 2, 1 triple 2 and so on. If we continue the number, there will be no repetition and non-ending. So these types of numbers are called irrational numbers. On the further chapter we will understand irrational number and rational numbers on a detailed basis, right? Now you have to understand there is no such number which is rational and irrational at the same time. Now if we remember that there are numbers which at the same time are whole numbers, are integers, or natural number. That is, if I talk about 5 is also a whole number, 5 is also an integer, 5 is also a natural number. So there are numbers which can satisfy all these types of conditions, but there is no such number which is at the same time rational and at the same time irrational, because the definition of rational and irrational numbers are exactly opposite. This is why you have to remember that there is no such number which is at the same time rational and irrational number. Now if we look into the diagram, you will definitely understand this oval shape is exactly outside of the rational number. This is the box of the rational numbers, which includes natural number, whole numbers and integers, but does not include these types of number, that is root 2, root 13 types of number, that is square root of non-perfect number, transcendental irrational number and non-repeating non-terminating numbers, right? Now what are the real numbers? This is the chapter of what we are discussing. What is the real number? Real number includes all the rational numbers and irrational numbers. That is the numbers which are in that box, that is blue colored box, and the numbers in brown box. All these numbers together called real numbers. So real number includes the natural number, the whole number, the integers and the rational numbers and irrational numbers. All these kinds of numbers are included in the large circle. This is the circle of real number. So you have to remember that natural numbers, whole numbers and integer are all parts of the real number. So in our general basis, until we get in the class 11 and understand the complex number, the number we can think are all real numbers, right? This is the basic concept of our real numbers. Next we will discuss Euclid's division lemma. Now Euclid, to remember and understand Euclid's division lemma, we must have the clear concept of the number system, what we have already discussed. Now what is the statement of Euclid's division lemma? Before going to the lemma, first you have to understand what is lemma. I think all of you are known to the fact that what is lemma. Still I will make a quick recap of the definition of lemma. What is lemma? Lemma is a proven statement used for proving another relatively large statement. That is a statement which is proved earlier, and we will use that to prove another theorem or large statement, right? This is called lemma. So Euclid's division lemma is one such of lemma which we will use in further chapter or in further application where we are going to prove the different concept and application. Now for any two, what is the statement of Euclid's division lemma? Euclid says that for any two positive integers a and b, there exist whole numbers q and r such that a equals to bq plus r. Now in many of your books or internet, it is written that there exist not whole number, there exist integers. This is also true, there exist integer, but in most general case, these two numbers q and r are whole numbers. What is the difference between integer and whole number? I think you can remember that. That is, integers include negative number, but whole number does not include the negative numbers. So there is a certain difference between integers and whole number. But the actual lemma says that there exist whole numbers q and r, right? Now let us understand what the lemma says, and with certain examples. The lemma says that if we are given with two positive integers, right? Suppose I give you two positive integers. Suppose a equal to 2 and b equal to 3. Now if I ask you to write so it says that for any two positive integer, we can write it in the form of a equal to bq plus r. Now if we have, as we have taken two positive integers, so we can easily write them in the form of Euclid's division lemma. So we can write 2 as 2 into 2 equals to 3 into 0 plus 2 form, where 2 is our a equals to b into q plus r. Now we have to understand whether this satisfies our condition or not. What are the conditions? 0 less or equal to or less or equal to b. That is, r must be less than b and greater or equal to 0. Now here r is 2. Now r is 2, definitely less than 3. Now 3 is act as b. So r less than b satisfies. Also 2 greater than 0. So r satisfies the given condition. This is why we can write 2 as 2 equal to 3 into 0 plus 2. This is why Euclid's division lemma acts. Now if I take another example, suppose a is a bigger number 10 and b is a smaller number, suppose 3. Now if I try to apply Euclid's division lemma here, we can write 10 equals to 3 times 3 plus 1. So a equals to 3 means b, and here q is also 3 plus r. In this time also q and r satisfies the given condition. R is 1, which is less than 3, which is b also greater than 0. Also if the numbers are completely divisible, right? Suppose a equals to 10 and b equals to 2. In that scenario, we can write 10 equal to 5 times 2 plus 0, that is a equal to bq or qb, that is the multiplication is commutative, right? You have know that, plus r. So in that scenario, r equals to 0, which is also less than b, that is 2, and satisfies the condition greater equal to 0. This is not the greater, this is equal to 0. So any two types of numbers, whether two numbers, the a is small or large than b, that doesn't matter. Whether a is completely divisible by b or not divisible, that doesn't matter. So for any two positive integers a and b, we can write one number as bq plus r in that form, where q and r must be whole numbers. Whole numbers means they must be includes 0 and all positive numbers. This is Euclid's division lemma 6. Now understand Euclid's division algorithm. Before that, first we have to understand what is algorithm. Algorithm is a series of well-defined steps to solve a problem. Suppose you are given with a certain problem of fixing an electronic device. Now if you know that how to open the electronic device and how to repair that and how to again fix it, then you can easily understand the process of fixing that electronic device and correcting the errors. So this is called a electronical algorithm. So algorithm is a series of well-defined steps by which we can solve a problem. Now here Euclid's division algorithm represents a series of steps or techniques to find the highest common factor, that is HCF, of two positive integers. So if we are given with two positive integers, we can use the Euclid's division lemma to find the HCF of the number. Already we have know that to finding the HCF, different types of process of finding HCF in the lower class, like we have learned that in class 5 or class 4 level. So we can apply that process, so you can easily find the HCF. But in that scenario, we will apply Euclid's division lemma to find the HCF. Now you can all definitely cross check the answer by your existing knowledge, right? Now what the steps or algorithm Euclid says? Euclid says step 1, let a and b are two positive integers, and definitely one number will be greater than the another number, right? If they are not greater than, so we can easily find the HCF, right? Suppose you are given the two numbers, both of them are 2, so we can easily write 2 as 2 into 1 plus 0. In that case our HCF will be 2, right? So if this is the case, so in that case this is a simple process. Now if this is not the case, suppose one number is greater than the another number, then by Euclid's division lemma we can get q and r, because we have already understand that by Euclid's division lemma it states that if there is a two positive integer, we can definitely get two other numbers q and r such that one number can be written as bq plus r form, where r satisfies the condition. As a is a larger number, we can definitely write a as bq plus r form, where r must be less than b. What is the next step? Our next step is, if this r, that is the remainder, if the remainder is 0, then HCF will be the smaller number, that is b. Now if the remainder is not 0, now if it is looks like complicated to you, I will explain this on details on the later chapter, right? Now if r not equal to 0, then apply step 3. What is the step 3? Then apply Euclid's division lemma again for b and r. What are the b? B is the divisor of the previous step and r is the remainder of the previous step. And when we apply Euclid's division lemma for b and r, we will get another two numbers. Now you have to remember that in the case of b and r, b is greater than r, so we can apply the division lemma, right? So we can get two integers or two whole numbers s and t such that b can be written as rs plus t, where t will be the remainder when we will divide b by r, right? And s will be the quotient. Now in that step, if t, the remainder, is 0, then HCF of AB will be the r, that is in that step the divisor will be the HCF. Now if t not equal to 0, again apply the Euclid's division lemma for the remainder, that is in that case this is t, and the divisor, in that case divisor is r. Again apply the Euclid's division lemma. Again we will get two numbers, suppose m and n, and we can write r as mt plus n. In that step, if n equal to 0, then our HCF will be t, HCF will be t, and if not equal to 0, we have to follow the we will continue that process until we get the remainder as 0, because whenever we get remainder as 0, in that case we can say that the HCF will be the divisor, right? So we have to continue the process until we get remainder as 0. Now let us understand this Euclid's division algorithm with some example. Suppose there are given two numbers, find the HCF of 12 and 40 using Euclid division algorithm. First we have to understand which number is greater and which number is smaller. You can easily say that 40 is greater than 12. Now by dividing 40 with 12, we can easily get 12 3s are 36 and 4 as remainder. So we can write 40 as 12 into 3 plus 4. So we can write A equal to BQ plus R in that form. Now R is, that is 4, less than 12, that is B, and definitely greater than 0. So satisfies the condition. Now as the R, that is the remainder, not equal to 0, R equal to 4, that is not equal to 0. So according to Euclid's division algorithm, we have to apply again Euclid's division algorithm for the divisor and the remainder. Here the divisor is 12 and the remainder is 4. Again, if we apply Euclid's division algorithm, here you can easily understand that 12 is greater than 4. So we have to divide 12 by 4. 4 3s are 12, here is 2. So there is no remainder. So we can write 12 as 4 times 3 plus 0. So in that case, we get that remainder as 0. Now if we get remainder as 0, Euclid division algorithm says that the divisor will be the HCF. What is the divisor? Here 4 is the divisor. You can easily see that 4 is the divisor. So HCF of 12 and 40 will be 4. Now if you check cross check your answer, you can you understand that we write 12 and 40, we can divide it by 2, 2 6 are 12, 2 20s are 40, again divide it by 2, 2 3s are 6, 2 10s are 20. Now we cannot divide further because there is no common factors of 3 and 10. So we can say that the numbers which resides on the left of this division are called the HCF. So 2 into 2, that is 4 is the HCF. So we have get the correct answer by Euclid's division algorithm. Let's take another example which is bigger than that. So if you are given with the number 612, that is 612, and 1314, using division algorithm we have to find the HCF. So first, what is the first step? First step is to determine which number is greater. Now we can easily understand that 1340 is greater than 612. So we have to divide the larger number by the smaller number, that is 1314 divided by 612, 2s are 1224. If we subtract 0 9, right? So we can write 1314 is equal to 612 times 2 plus 90, that is in the form A equals BQ plus R. Now this time R not equal to 0 because 90 not equal to 0. So according to division algorithm, we have to apply again division algorithm for the remainder, that is 90, and the divisor, that is 612. Now in between them 612 is greater than 90. So we have to divide the larger number, that is 612 by 90. So 96 are 5, 40, to remainder 11, 72 is the remainder. So we can write 612 equal to 90 times 6 plus 72. Again in this scenario 72 is the remainder and which is R not equal to 0. So again we have to apply the Euclid's division algorithm for the remainder, that is 72, and the divisor, that is 90. So we can easily understand that 90 greater than 72. So we have to divide 90 by 72. 72 ones are 72, remainder is 18. So we can write 90 equal to 72 times 1 plus 18. Again the remainder is not equal to 0. Apply the division algorithm for the remainder, that is 18, and the divisor, that is 72. Now you can understand that 72 is greater than 18. So So we have to divide 72 by 18. 18 4s are 72 and the remainder is 0. So we can write 72 as 18 times 4 plus 0. Now in this step the remainder becomes 0 after 4 steps. So we can say that what is the HCF? HCF will be the divisor. So in the last step, what was the divisor? Divisor was 18. So HCF will be 18. You can easily cross check what we have cross checked in the earlier example. By similar argument you can check the cross check the HCF, and you have, I think you have understand how division algorithm works and how by division algorithm we can find the HCF of two given positive numbers, right? Next, some of the examples are given to you on your screen. Pause your screen and write it down on your paper or notebook, and you try it yourself, and let me know in the comment section that whether you get the right approach and find the correct answer or not. Next, understand fundamental theorem of arithmetic. What is the fundamental theorem of arithmetic? Before going to that, you have to understand what is prime numbers. Already you have correct knowledge of prime numbers, but I want to make a quick recap or quick understand what are the prime numbers. Prime numbers are such numbers which has exactly two factors, 1 and the number itself, and you have to remember that 1 is not prime, right? So the smallest prime is 2, and which is even prime, and any other prime number which occurs other than 2 are of odd primes. Only even prime is 2, right? So fundamental theorem of arithmetic says that every composite numbers which is not prime, you have to remember that every composite number can be expressed uniquely as a product of primes except for the order in which their primes occurs. Now this might looks like a little bit of difficult, that what it says, what the statement says. So I took 3 examples. You have already looked into the screen that 45, 32 and 150. I can easily explain you what the theorem states. Before jumping into the examples, once again read the statement. Every composite number, so the numbers which are not primes, can be expressed uniquely. Uniquely means there will be no other expression in which we can express the same composite number. So there will be unique representation of the composite number as a product of primes. Now as a product of primes, there is a concept. If the prime occur 2 times or prime occurs 3 times, which will be occurred in our examples, then whether it will be composite, it will satisfy the fundamental theorem or it will not. Definitely it will satisfy the fundamental theorem. This is why it is said that except for the order in which these primes occurs. So if the primes occurs multiple times, that doesn't matter. So the expression must be unique. So if we express one number and it gives us certain prime, suppose 2 5 times, and we express the same number in different types, so it cannot have more than 5 or less than 5 times 2. So it must be uniquely expressed. Let us jump into some example to have a better knowledge of this fundamental theorem of arithmetic. Now if we factorize 45, we can easily get that. First of all, by using 45 factorization of 45, we can easily divide it by 9. So we can definitely start with 9, but we have to remember that we are going to factorize as product of primes. This is why we have to start dividing with primes only, right? 9 is not prime, definitely 9 is composite numbers, we have to divide with primes. So the first prime which will divide 45 is 3. 3 15s are 45, again it is divisible by 3, 3 5s are 15. Now 5 is divisible by 5 1s are 5. So we can express 45 as 3 into 3 into 5 into 1, that is 3 square into 5. So 1 doesn't make any sense because we can write multiple times 1, that doesn't make any sense. So 45 can be written as 3 square into 5. This is the unique representation of 45. Now you cannot express 45 in other way. Now you can say that we can write 45 as 9 into 5. Also we can write as 15 into 3. Yes, this is also the expression in which we can write 45. but these are not the product of primes expression, because 5 is prime, 9 is not. Similarly, 3 is prime, but 15 is not the prime. This is why the prime factorization representation of a number will be definitely unique representation. Now, what is the exception? The exception says that except for the order in which the prime occurs, that is, in that case 5 occurs 1 times but 3 occurs 2 times. So the order of 3 is 2. That doesn't matter. Here you can say that here 3 occurs 2. So in the later example there will be number which occurs multiple more than 3 times. So this doesn't matter, and this does not affect the uniqueness of the expression of the composite number. So this is the exception says that. So the primes can be occurs in multiple times. So the order of the primes can be more than 1 time. So not necessarily there will be 1 time that occurrence of the prime. So any prime number can be occur multiple times. So that doesn't matter. So if I try the next example, so 32 will be divisible first prime by 2. 2 16s are 32, 2 8s are 16, 2 4s are 8, and 2 2s are 4. So we can write 32 as 2 into 2 into 2 into 2, that is 5 times 2 to the power 5. So this is the unique representation of 32. You cannot write 32 in different way where the numbers will be prime. Now 2 to the power 5 is not prime. This is the exception says that 2 is prime, and prime can be occur multiple times. This is why it is said that except for the order of the primes. But now if you ask that we can write it 2 to the power 3 into 4, this is also the expression of 32, but in that case 2 is a prime which occurs 3 times, that is allowed in the fundamental theorem, but 4 is not prime. So this is not the unique representation what we are looking for. We are looking for the prime representation. So prime can occur multiple times, but composite number cannot occur multiple times, right? Now if I jump into the next example, the first number which will divide 150, that is 2. 2 75s are 150, then 3 25 75, and 5 5s are 25. So 150 can be represented as 2 into 3 into 5 square. There is 2 5, this is why 5. So this is the unique representation of 150, in which we can represent is as the product of primes, where 5 is the prime which occurs 2 times. This is allowed in the fundamental theorem of arithmetic. So as it allows the order of the primes. I think you understand that fundamental theorem of arithmetic, right? Next, using fundamental theorem of arithmetic, that is the expression of a composite number as a product of prime, we can easily find the LCM and HCF of given numbers. So next we are going to discuss the finding of HCF and LCM using prime factorization or fundamental theorem of arithmetic. Now what is LCM? LCM is least common multiple. And what is the process to find the LCM of given numbers or two numbers? Product of all primes with highest power. Now if we factorize two numbers and factorize as a product of primes, so the product of all primes which occur in these two numbers, and we have to take the highest power of that prime, right? That will give us the result of LCM. And what is HCF? Product of common factors. So if we factorize these two numbers, they will uniquely represented. So if there exists any prime number which is common to them, that is any number which is common to them, so we have to take that number with their lowest power, and by making their product we will get the HCF. This is the process. Now let us understand this process with some example. Now first we are going to express 36 and 54 as unique representation of prime by using fundamental theorem arithmetic. So we can write 36 as 2 18, 2 9, and 3 3. So 36 can be written as 2 square into 3 square. Again 54, 2 27, 3 9, 3 3s. So 54 can be represented as 2 into 3 to the power 3. Now if I find the LCM of 36 and 54. It will give. Now let us understand the product of all prime factors. What kind of prime factors occurs in this example? 2 and 3, and with their highest power. So we will write 2 and 3 and their product. Now their highest powers. Now 2 has power 2 in the 36 and 2 has power 1 in 54. So what is the highest power? That is 2. And for the case of 3, 3 occurs 3 times in 54 and 2 times in 36. So what is the highest power? Highest power is 3. So we have to take both the numbers and all such prime factors occurs in that number and their highest power. Then we have to make a product to find the LCM. So here is the LCM. 2 2s are 4 multiplied by 3 3s are 9 into 3, that is 27. 27 into 4 will gives us 108. Right, this is LCM. Now what is HCF? According to the definition, HCF of 36 and 54 will be the product of common factors. Now these two numbers has common factor 2 and 3 because both the number have the prime numbers 2 and 3. So we can write 2 multiplied by 3. Now we have to understand what is their lowest power. In the first example, that is first number 36, 2 has 2 powers, and in the 54, 2 has power 1. So what is the lowest power? That is 1. So for the case of HCF, we have to take lowest power of 2, that is 1. And if we take the 3, 3 has highest power 3 and the lowest power 2, right? So we have to take the lowest power, so 2. So our HCF will be 2 multiplied by 3 3s are 9, that is 18. This is the process of finding HCF and LCM of two numbers using their prime factorization. So I think you have to understand the process. Next, relation between two numbers and their LCM and HCF. I have taken the same example so that it becomes easier to make you understand and the concept becomes much more easier. What is the relation? If we are given with two positive numbers, then the product of the numbers will be equal as the product of their LCM and HCF. And the second says that HCF always divides LCM. So highest common factor always divides least common multiple. Now you have to remember that the relation 1, that is product of numbers equal to LCM and HCM, always holds for only two numbers. I will give an example where this relation does not hold if we take three numbers, right? So first let us understand how these products how these two relations are true for our previously given example. Now if I talk about the previous example, we have already get that LCM equals to 108 and HCF as 18. So find the for the first relation we have to find the product of the numbers. So the numbers are 36 multiplied by 54. Now let us do the multiplication. 54 multiplied by 36, 6 4s are 24, carry 2, 32, 3 4s are 12, carry 1, 15, 16, so 4 4 9 1. So 1944 is the product of the numbers. Now find the LCM multiplied by HCF, that is 108 multiplied by 18. 18 8s are 144, 4, 18 zeros are 0, 4, carry 1, 18 ones are 18, 1 19. So it will give us 108 multiplied by 8, 1944. So you can easily verify that the product of the numbers and the product of LCM and HCF is equal, and this holds for any two positive integer. So the first relation is true. Now if I take the second relation, that is HCF divides LCM. Now our HCF is 18. We have to make sure that that divides the LCM 108. Definitely this is true. If we divide 108 by 18, 18 6 are 108. So it is completely divisible. So this is also true that HCF always divides LCM. The fact behind this, that is HCF takes the lowest powers and LCM takes the highest power. So always lowest power definitely divide the highest powers of the numbers. This is why always HCF divides LCM, and in that case HCF divides LCM. This holds for any 2, 3, 4, what kind of number you take, this will always hold. So if we take 4 numbers and put out their HCF and LCM by the previous method we have already learned, so we can easily verify the second relation. But the first relation does not hold for 3 or more numbers, it will only hold for 2 numbers. Let us take 3 numbers, that is 2, 3 and 6. Now what is their HCF? HCF of these 3 numbers equal to 1, because they don't have common factors except 1, so HCF is 1. And LCM of these numbers are 12, because 12 is the smallest number which is divisible by these 3 numbers. This is the LCM. You can easily find that applying your existing knowledge, right? Or you can find their LCM by prime factorization method, no problem. But this does not hold that this does not hold satisfy the first condition. Now if I take the product of the numbers, this will gives 3 into 2 into 6, that is 36, right? Now if I product the HCF and LCM, it will give 1 into 12, that is 12. So 12 does not equal to 36, so first relation does not hold for this 3 numbers. So we get different kinds of example. There are some numbers of 3 numbers or 4 numbers which satisfies this condition, but there are only very few numbers are that. There are numerous numbers which does not satisfy the condition. So universally we cannot say that the first relation holds for more than 2 numbers, right? But the second relation always holds. Now in that case LCM is 12 and HCF is 1, that is 1 always divides 12. This is trivially true. But if you take any other example, the second relation definitely hold for any number of numbers, right? So these are the basics of number system and the real numbers. On the next class we will detail understand the rational and irrational number, the transcendental irrational numbers, what kind of rational numbers are there, what is their relation, how rational and irrational number can be make their operations, that is addition, subtraction and their division. We will find the rational number in between irrational number and irrational number in between rational number, and their different kind of application. We will also prove certain given number, that is square root of non-perfect square as irrational number. We will all learn in the next class. So stay tuned and keep practicing.